All right, our final example with respect to work is the leaky bucket example. So we've got a situation where we've got a pulley and a rope that's pulling up a leaky bucket. And it says here that the bucket itself weighs 5 pounds and the rope weighs 20 pounds. Now that's the whole rope. So if you think about it, what's going to change in this situation is that as we pull rope in, the amount of rope remaining to pull in weighs less. Okay, so that's why they say the rope weighs 0.08 pounds per foot. And then they start with 2 gallons of water, which, by the way, is 16 pounds. And the water is leaking out at a constant rate. So there's a lot of stuff going on in here and a lot of stuff changing. Okay, and we're told, by the way, the water finishes draining out just as it reaches the top of this 20 feet. And at that moment, there's just a 5-pound bucket of water and no water, or 5-pound bucket that is empty with no water in it. So what we're going to do is look at lifting the work required to lift just the water, just the rope, and just the bucket. Split it up into those 3 and then add them all together to get your total amount of work needed. So the first thing we're going to do is figure out how much work is required just to lift the water. Now, at the beginning, there is 16 pounds of water. At the end, there is 0 pounds of water, okay? So we're told that the 16 pounds of water trickles away over 20 feet. So what we're gonna have here is that we have 16 pounds divided by 20 feet, okay? And then over time, or as the bucket goes up, it loses water. So this is going to be multiplied by 20 minus y, and that is in feet. So basically, when I cancel out these, I'm going to be left with the number of pounds of water. So 16 over 20, of course, is 0.8, and 0.8 times 20 is 16. 0.8 times the negative y is just minus 0.8 y. So this is the weight of the water dependent on how far the bucket is off of the ground. Okay, so the way to integrate this is basically to say we're going to integrate it from 0 to 20, and we're integrating 16 minus 0.8y dy, and this is going to give us the work required to lift just the water. So I integrate like that, and then I evaluate from 0 to 20. That's a 2 right there. And when I integrate all this, what I'm going to get, 16 times 20 is 320, and then I'm going to get 0.4 times 400, which is 160. So I have 320 minus 160 is 160 foot-pounds, okay? So what I've done here is I've basically taken the ratio of how many pounds of water leak out over a certain distance, and then multiplying that by the changing distance, and I integrate and I get out the work it required to just lift the water, okay? So the next thing we're going to do is lift the rope, and the rope is another variable force problem because as we pull the rope in, less rope needs to be pulled in, so the force required to pull it is less. So here we're told there are 8.8 pounds per foot is the weight of the rope. And then how far are we pulling it up? Well, same distance, 20 minus y, and that is in feet. So once again with my units, my feet will cancel. And what I need to integrate is, let's see, 0.08 times 20 is 1.6. And then 0.08 times negative y is 0.08y. And I'm going from 0 to 20. And when I integrate, I get 1.6y minus 0.04y squared from 0 to 20. And when you put that in your calculator, or you can do it in your head, either way, you're going to get 16 foot-pounds that it took to lift the rope. So far, we've had 2 variable weight problems, one lifting the water, one lifting the rope. Now we have a constant force problem because the bucket weighs 5 pounds throughout. So this one's a bit easier. Remember that constant force is just work equals force times distance, and force is 5 pounds here. Distance is 20 feet, and that's going to give us 100 foot-pounds. Okay, and then the total work to lift them all, I just need to add them up. 160 foot-pounds plus 16 foot-pounds plus 100 foot-pounds gives us 276 foot-pounds to lift the entire leaking bucket of water.